Hello everyone, it's November 11th. Alright, let's get into it. Bus routes. Maybe it's an old problem again. Let's take a look. Bus routes. I smell like food. Oh, maybe it's a new one. You are given an array of routes representing bus routes, where routes I is a bus route that the ith bus repeats forever. For example, if routes 0 is 157, it means that the 0th bus travels in sequence 157, 157, whatever. It will start at the bus stop source. You are not at any bus initially. I'm gonna go to bus stop target. You can travel between bus stops by buses only. To the least number of bus you need to take to travel from source to target. At a -1 if it's not possible. Interesting question. We have 500 routes, but each route can be 10 to the 5th, so it's a large cycle. Total number is less than 10 to the 5th. This doesn't matter. This doesn't matter, okay? So I have bus 1 is 1, 2, 7. Bus 2 is 3, 6, 7. Then we need to take from source to target. So we need to take bus 1. And we just want a minimum number of buses. So source 1 can take this, it doesn't matter. And then we take this. First bus to bus stop 7. And take the second bus to bus stop 6. Interesting. The second one, we have a lot. We have 7 and 12. 4, 5, 15. Probably is not the best one to represent it because 15 need to go back, right? So let's redo this. 7, 12. Okay, so 7, 12. 4, 5, 15. 4, 5, 12. Oh, 15. I say 15. 6 to itself. 15, 19. And 9, 12, 13. 9, 12, 13. And we want to go from 15. I know. We want to go to 12 because they are not connected. Therefore, no go. Well. We can create a map of adjacency list, right? Basic adjacency list. Now 7 go to 12, 12 go to 7. And then we traverse through them. Make sure we don't go back to the one we have gone before, so we can get a bunch of... So we can get all the bus stops that are connected. Right? Bunch of bus stops that are connected together. And if the source and the target are not in the same connected graph, then it's impossible. Just like this. Right? 15 and 17, 15 and 12 are not together, which I think will be easier to solve if we use, union find, right? We can use union find. 7, these together, all of these, put them together, 4 and 15, 4 and 15, right? 6, well, by itself, 15 and 19, so they will all be together, and they will be together, and then we just say, if the parent of source 15, right, if the parent of this is equal to parent of this, if they're equal, then at least we know we can find a way, otherwise we cannot. So that's an easy problem. But now let's say we know that they can be connected. Then how do we find a route to connect them? Well, if they belong to the same bus route, then we're going to take one. So we need to go to check 15, which bus, which route it belongs to. Well, to do that, we can do 10 to 16. I mean, it's fine. We can use map, a dictionary, right? So each one belongs to a few. So we check 15. So we can have a list. Okay. Like we check 1, we have a list. So 1, it belongs to 0, right? 1 belongs to route 0. 6 belonged to route 1. Okay. Then the question is from 0, route 0. The route 0 is something, right? And the route 1 is something. Now we need to know how many more buses do we need to take in order to get to route 1, right? That's what we need. How many more do we need to take? How do we know that? Now what we need to know is the route itself. How are they connected? So there are like 2 levels of connection, right? One level is the stop to stop. But I think the stop to stop is easier to solve. Like I said, we're going to do our union find. Maybe we don't have to do union find. We find which route they belong to, then what we need to do is find the connections between the routes, right? So basically, we need to know if they share. If two routes share, then how do we know if the 2 routes share? That is a good question. We need to know the mapping between the routes. So like this one, the mapping will be 0 to 1, right? 0 to 1. This mapping will be 0 to 4, 0 to 4, and 2 to 3, right? That's its mapping. But how do we do this mapping? We probably don't even need union find if we can find the mapping among the routes. So each route we have these. So basically we're saying which routes share the same. Well, I mean, we can go with this, right? 7 has 2, right? It's 0 and 1. 7 has 1. So we'll do all of the stops. Okay, we do all the stops. For each stop, we list how many different routes it belongs to, right? And then when we've done that, any routes, any stops that's associated with more than 1 routes, that is the connection. Then we can do a adjacency list for the routes. So 0 we can say to 1 and 1 to 0, right? And then blah blah blah. So we have an adjacent, we have a graph of routes, right? A graph of routes. Once we have a graph of routes and we know that the source belongs to a route, the target belongs to another route, then we just need to find the shortest path, right? The shortest path to get to there. That's just the shortest number of routes. And that can be solved by BFS. All right, we have a strategy, and I'm going to Python it today. No problem. Let's Python this. (11:11). Singles Day. Oh shoot. It's not 11:11. Ah, screw me. I mean, maybe you can do, you don't need to do, do you want to Java it or? I mean, it's, yeah, maybe we can Java this thing. Yeah, I think you already have the idea, and I don't think it's that complicated. It's all right, right? It's all right. It's all right, but we're gonna Java this. Yeah, let's Java this. I think it's okay. All right, let's Java this. Java this baby. Java this baby. Why do we have a, I don't know. Like why there's an extra, right? It doesn't make any sense. Can we do this? There we go. There we go. Okay. All right. So what do? Well, we first create a stops, right? Stops. So we need to do. What do you want to do? 10 to the 6. You can make a list of lists. That's a hash map. That's all right. So let's say map integer list integer. We call it stops to route. Right, that's fine. Then we'll go through all the routes for int I smaller than routes dot length I plus plus. All right, so each route we can have the stops. So say int stops equal to routes I. Then for int stop of route as a hash map. So it's a stops to route dot put if absent stop 0. No, just stop. New array list, right? Then stops to dot get stop dot add I. Boom. So we'll do this. Now I finish, then we go through stops to route. We don't really care which stop causes. All we need is just to produce the graph. Now we need a graph. And this graph will be a map as well. Integer and list integer. This is a route graph. Right, we have 2. Now for the route graph, we can. Oh, we don't need. We can use a list of list. Honestly, right? I think we can use a list of list because it's only 500, so we can save the effort Okay. Let's use a list of list. So it would be a list of list will be new array list. Right? Then we say route for int I equal to 0. Initialize it. I smaller than routes.length I plus plus. We can say route graph dot add new array list. Boom, done. Then we don't go through the stops, right? Then we say for list integer routes. We have routes already. We need a new name. Connected routes. Just R's of stops to route dot values, right? So we get the values R's. Then we need to go for each of them. If there are a couple connected, we need to run every single pair. Oh, this is where it gets really ugly. All right, every single pair. So for int I equal to, it's fine. I small rs dot size I plus plus, right? Every single pair. For int j equal to 0. j equal to I. No, j equal to I plus 1. J smaller than rs dot size. And j plus plus. Every single pair. So we need to do route graph dot get I dot add j, right? And then route graph dot get j dot add I. Right? That's what we have to do. Go through all the routes for each route, every pair, right? We need to find every pair to make sure that we have two ways. So now all we've done, then we'll BFS to find the smallest, shortest path from source to target. But hold a second, we can avoid doing this, right? If after doing that, we can make sure if they, actually we don't know at this point, so we have to do BFS, right? We have to do BFS. So we have the source, so we go into source graph, right? So we need a queue. But we don't like to do it this way. So I will just use array list. Well, I'll use the list integer. Alright, integer q equal to new array list. Okay. And then we say q equal to, can we do something like, that's alright. We can just say for int r of graph dot get source, right? And q dot add r. That's okay. Collection dot add all. Perfect. Teach me. Q dot add all dot get source. I already did it. Replace add all can be removed as a constructor call. Wow, tell me, show me. Nice. All right, so that is the queue, right? And then what we need to do is while not queue dot is empty, right? If queue is not empty, then we need to go through everything inside the queue, and now we find, so we have to say int res equal to 0. So we're trying to find that is actually okay, right? It will be, because at least it has to be 1, right? So we start with 0. And if we reach the end, then we return, right? We go through everything inside the queue, right? We go through everything inside the queue. Then we go for the next one. Once we find out, right? Once we find out the target is reached, right? Once we reach the target, then we shall return res plus 1. I think that looks good, right? So we have to say a list integer, we have a temp, okay? So every time temp, we go to new array list. Right, temp will be new array list. And then for int route of, we need to know which route has target 6, which means it might be better if we don't use array list here. Maybe we should use a set. What do you think? We use a set. Hash set. We can add as well, right? I think this queue is array list. Okay, so that's fine. All right, this is fine. Now we just say for each route inside the queue, if route graph dot get, no, not route graph dot get, not route, it's the stops to route. It's the stops to route. This is a set. This is still a list. This shall be hash set. Okay. And this is array list. And this is a set of routes. That is okay, right? A set of routes. That's actually not right. Okay, it's a little bit. So hold on. So we will put stops to route. Okay, stop dot add. These are routes, right? These are the routes. So we have the routes in it. Then we have the route graph. Okay, it's perfectly fine. Route graph. And then for the routes, these are the set of routes. So within these routes, we need to, that's not INJ, right? This is routes. So we need to turn this into a list. Okay? We're going to turn this into a list. So we just say list integer. List integer rs list equal to new array list. Can we put rs in here? I think we can, right? And then for this INJ, it's not I, it's rs list dot get I. This rs list dot get j. Okay, INJ is just the indices, and we need to use the rs list, right? We need to use the rs list, and then rs list dot get j and rs list dot get I. Okay, so blah blah blah. Once that is done, right? Then I wonder if this. Yeah, we'll do this later. Then we have a temp, we have a res, blah blah blah. So in R in the Q, that's the route, right? We have a route, and we say if R is the target, so we need to have that's not a route graph. The source is that, right? So we should be stops to route. Stops to route, we get a bunch of routes, right? Bunch of routes. And then for each routing queue, we need to do stops to route dot get destination. So we shall probably, yeah, that's not, I'm gonna change this one more time. Sorry. Hash array list. Yeah, it's okay. Just, you know, you don't need this, and you call it list, right? What we need here is a set of integer. Here's a new set, new hash set. Not hash map. Hash set. Hash set stops to get destination target. That will tell us the routes, right? That will tell us the route. So say target routes, okay? And then what we need to do here is just to check. We say target routes dot contains R. If it contains R, we'll return rest plus 1. We're done, right? If it does not contain R, then we need to, because R is the route, right? So we need to find all the other routes, right? All the other routes. We probably also need a scene, so we need to say set integer scene equals to new hash set q. Okay, so these are already seen, right? That is okay. Right, that is okay. And then R, get out. Okay, then we need to get the children of R. So for int child of, now we do route graph dot get R. Okay, and then we say if scene dot contains child, right? If the child has not been seen yet, then temp dot add child, right? And scene dot add child. So child gets added to both, which means next time it's the same one, it won't be happen again. So blah 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 blah. Once we're done, okay, then we do q is equal to temp and rest plus plus. Right, blah blah blah. If we find it, we return. If we haven't found it, we return -1. All right, so that's how I will do it. Let's give this a shot. Just use the first one. If it's not right, we will correct it. Okay, first one's correct. Let's try both. Both are correct. I don't like this, so I'm gonna do RS. Basically just trying to make it a little bit shorter. I have a queue, I have a temp, I have a scene, I have a target routes. And then we just want to check the target routes. We can go, give it a shot. And the answer is bad. Expect a 0. Ooh, what is this? 0. Oh, Is that a special case? That is a special case. Source is equal to target. Turn 0. Yeah, you're already there, so you don't take any bus. If you even take 1, you have to take 1 bus. Actually, we can try that, just to make sure that we are on the right path. Like, let's say if from 1, you're gonna go to 2. That at least need to take 1. Right, you have to take 1. Yeah, you have to take 1. So, that's an oversight. Didn't think about that. Now we have a runtime error. That is interesting. Target routes. The target is not in any route? What? Oh my goodness. My goodness, what the hell is this? No pointer, can't invoke the size because C is null. Are you telling me that I'll use this as example. Are you telling me if I do 0, which just doesn't exist in anybody, that's why I have this error? Yep, that's why you have this error. But this one is 2 array. This one is error in different places. It's error in different places. I mean, I guess it's because if I do it here, it will have the same error. Yeah. So basically, one of them is not inside. That is very interesting. That is very interesting. So basically, I think what I need to do is after this is done, we need to check. Right? We need to check. Check for what? Check to see if so we can say if route no, not route, stops to route. Is that like contains or what? What's the API for this? If stop to route dot contains key source, right? If it does not contain key, or it does not contain, yeah, that's also my oversight. Should have noticed it contains key target. If any of this, that means it's gonna be impossible. I return -1. Seems very reasonable to me. Yeah, so we will try this. Pretty sure that's why. Ah, we passed a lot, so I think we'll use this, give it a shot. If it passes, I think that shall be it. Yep. I have confidence I'm gonna write some stuff here. What should I write? 815, right? Find the routes that contain source and the routes that contain target. Use the routes array to construct a graph for all the routes. Then use BFS to find the shortest path from any route that contains source to any route that contains target. Two tricky part. First, if source is equal to target, we don't have to take any bus. Second, if source or target does not belong to any routes, it is not possible to reach from source to target. Yeah. So runtime. So we have to go through let n is equal to len routes. M is equal to total number of stops inside routes. Then we take OM, like this, total stops, including repetition. Alright, so OM is that, right? And then plus N, that one, plus, what's that one? That's the total number of unique routes. M prime, that's unique routes. For each unique route, no, that's unique stops. For each unique stops, we'll have, I mean, if you think about it, yeah, I don't even know how this, I think this is ON squared for this one, because you can go, well, it's hard to say, right? It's hard to say. Once you get this, it could be M, because you have to go M times, right? And then when M prime times N, it can be squared because you do it twice. So it's on that, right? And at the end, you have BFS. Every node is visited once. So it's routes, so that's M, not N. That's how I understand it. I see if it passes. Ooh, it is not. It's too slow. Too slow. Ugh. Alright, have to be smarter. Have to be smarter. Wait, hold a second. View all. I guess that's why it's hard. Yeah, at this point, we're basically trying just to get the answer. What's the answer for this? 3. So which part takes the longest time? Well, I think it's pretty obvious which part. This is okay. Okay, this is okay. This is okay. This is the routes. This is definitely okay. Right, what is not okay is this part. It just goes round and around too much. So we need to find a better way. Well, I'll find a better way. Like, here's what I think. Go back to the drawing board. there will be a lot of stops that's unnecessary in this path. So I think what we need to do is to go find this, right? Stops to route. So we have the source, and from the source we know all those routes. That's good. And then for those routes, they're all connected, right? Those routes are all connected. They're all connected to a single stop, right? To a single stop. So those routes are connected. Then we'll go, make them connect. And then we should just go from there. But how can we go from there? So we go to the next routes, and they are all connected as well. Good question. So the question is, who are they connected to, right? Hold on, let me think again. So what we have now is we have some stop. Have some routes, right? Each one connect to some routes. And our source have RS1, RS2, we have some routes. And then our target also have some routes, RT1, RT2, also RT, let's call it P, let's call it Q, right? So now the question is, from source, from these routes, how do we find a path, shortest path to go there? So the way to do is from RS1, we need to find which routes. Oh, some of them might be overlapping, right? If you think about it. No, I don't think they will overlap though. Because you have the routes are on a cycle, on a circle, right? And if I have, let's say, these sharing, right? If I have these three, that's sharing. So for this, I have these two. For this, I have these two as well. For this, I have these two as well. Yeah, I think for one thing we can make them better is not to the graph. Exactly, the graph. Because they might be, sharing, which means some of the edges gets repeated. So this I do think shall be a set. Right, this is a set. So we say new hash set. Right, a new hash set. So all the graph gets in is a set. So we can add. It's okay. So it won't grow in length. And then blah blah blah. So yeah. You fancy give it a shot? I fancy give this a shot. No. Let's just start from here. If this won't work. Really? Oh, yeah, because I didn't copy paste this thing. My bad, forgot. Still slow, huh? Yep, that's still not right. But overall, I think it's correct. And take a look at these. These will pass, no issue. So. TLE. I like to record this TLE. What do you think? Like, how can we speed it up? I mean, if our size is 1, this one it's only room once. I don't think that's causing us an issue. It's when they share a lot and we're looping them as well, right? Yeah, I kind of see how this one goes. Like if I have these, we have 2 routes. We have tons of stops here, and they all share. So once I get this to make these 2 routes together, I don't have to do this one again. I don't have to do this one, right? But how do we know that this one only has? That's a thing, right? Because this stop might have a connection with something else. This stop might have a connection with something else. So yeah, it's a real question. Union find. Maybe. Union find. How? How do you do union find on this? So these routes are all connected. So they will union them, right? I will union them. So yeah, for each one, just union everybody. But you union everybody, that doesn't tell you. So yeah, you can union everyone. That's fine, but doesn't tell you from where to where. All you know at the end is from some route you can reach another route, right? That's all you know from union. From this route and this route and this. All you know, like, okay, these routes are connected, right? That's all you know. These routes are connected, right? That route is connected. But you don't know the shortest distance. You don't know the inner workings among these routes. Yeah, you don't know which route connects to what. That's why you do this, adjacency list in trying to figure out. But maybe we're doing things we don't need to. But how do we know we're doing things we don't need to do? Well, we have stop to route, and we get the routes. So I have all the routes to 1. I have another route. So from that route, we get every single stops. And for each... No. I go from my stop, right? And then go to my stop. I have these are the routes. All the routes that contains this stop, right? I have these routes. And then I need to know what other routes they connect to. So I find a route. I can go through all its... Maybe that one will be faster, right? So basically, this is the source. Yeah, have all these routes. Then I go to this route, which is basically, if I go to this route, it's basically this. We go through all of them. All right, we go through all of them, which is essentially this part, right? You go through stop value. No, this is just among the routes, but you have to go through. Nice. For this, you find a route, and you go through all the stops in the route. You go back? You're here.
I know.
Oh, to go through all the stops. Okay, I can go through all the stops. And for each stop, I can check its route. I can check its route. So if it's not a route that's already in it, we can push that route in. If it doesn't contain, then I can push that route in. But you go to a stop, but the stop can have many routes. And you go to the next stop. The next stop also has many routes. But at least we don't go through all the stops, right? We only go to the stops that's relevant. So it's like this part and the BFS, you're combining the two together. Yeah, got all the routes. For each route, we take out all its stop. And then we check the stops. Yeah, we still have to go through all the stops though. Yeah, I just need to know which route it connects to. That's it. Right? And if the routes they connect to each other, I don't want that. See, that is an important part. That I don't want it to connect to each other. What do you mean by that? No, that's not. That's just a starting point. Yeah, it doesn't matter. We just need to know from this, what's the next route, right? For this, what is the next route? For each route, we want to know the next route. And they might not contain everybody else. So I think to go just from the routes, we can save some computation. So instead of doing this, right? So what if we don't do this? We have a queue, right? We get a source, get a temp, get this scene. We can say scene routes. Maybe we can also say scene stops. Because if it's the same stop, right? Because each stop we get the new routes out. Yeah. So it goes new hash set. Scene stops dot add source. Right? This one already seen. The rest got a queue, got a temp. So this is all fine. We don't have this. Okay? This is something we don't have. This is something we have to compute right now. So basically we have a route. Okay? And we need to go to get the stops. So for int stop of routes are, okay, so for these stops, right, and then we say if scene stops dot contains stop. If it does not contain stop, okay, scene stops dot add stop, and then for, hold a second.
What?
Also talk to my mom and dad. My mom got message me. All right, I'm back. Last push. Okay, so we add a stop, and then we need to say for the stop to route. For list integer, right? Routes of stop to route dot get stop, right? But this is stop. No. Int next R. That's that. Right, again, if scene routes dot contains next R, scene routes dot add next R, and then temp dot add next R. Right, this is from the current route. We take a look at all its stops, and for all its stops, we take a look at its stop, see if it has any next route, right? And then we put the next route in it. So we'll do that. And hopefully by doing this, we can, make the whole process faster, and then we eliminate the need to do this. So it's kind of, think of this like on demand, right? It's like on demand. It's still right. This one's still right. Is this one right? Maybe this is the way to go. Yep, this is the way to go. All right, that was good. But I have to end right now. Need to do something else. So great, we got this. I'll write the comments later. All right, I'll see you guys tomorrow. Adios.